We're going to start off by reviewing the complex numbers and taking a look at the complex numbers in the complex plane. After this review, there's going to be a second part to this video that will go through the polar form of complex numbers. Let's go ahead and start working our way through the review of complex numbers. Complex numbers are an extension of the real numbers. So as we start here with our review, we can think of complex numbers as the number 3 or as the number 5 plus 2i. I is defined as the square root of -1. When we're dealing with real numbers or the xy coordinate plane, we just say that this one doesn't exist, but we can create a complex plane where this guy doesn't exist. There's one more part to this definition, and that definition is how we treat squaring the imaginary unit I. I squared is equal to -1. So as we take a look at what a complex number is, it could be real. So this one is all real. Also complex though. This one here has both a real part and an imaginary part. And notice that I've abbreviated those with an RE and an IM for imaginary. We can also have a complex number that's purely imaginary. Something like -3i would be purely imaginary. On the complex plane, we are plotting the real part on the x-axis and the imaginary part lining up with the y-axis. So as I take a look at the examples that I started with, the number 3 is completely real. It has no imaginary part. So I would plot it here. The number 5 plus 2i has 5 for the real part, 2 for the imaginary part. So it's similar to the point 5, 2. So 5 for the real part, 1, 2 for the imaginary part. This plots 5 plus 2i. And then finally, we had the example -3i. So that would be -3 on the imaginary y-axis only. So this point right here is -3i. Let's go ahead and plot the examples in number 2. I'm going to go ahead and switch colors, and we'll plot those in green instead. So for number 2, we want to do 1 plus 2i. That's going to be 1 in the real direction, and then 2 in the imaginary direction. I should write imaginary there instead of 2. 2 is already there. So it's going to be similar to the point 1, 2. So 1 for the real part, 2 for the imaginary part, and we plot it right here. So this is 1 plus 2i. -5i is purely imaginary. So -5i is just the -5 on the imaginary axis, -5i. And then finally, we've got -3, -3i. This would be similar to the point -3, -3, but plotted on our complex plane. So -3 in the real direction, -3 in the imaginary direction lines up right here, -3, -3i. Finally, we want the value of that unlabeled point, which lives right here. So notice that the unlabeled point lines up with 3 on the real axis and -4 on the imaginary axis. So we would call that 3, -4i. So 3, -4i. Let's take a look at some operations with complex numbers. As we're working with the complex numbers, we can think of these really as like terms. So the real parts get added and the imaginary parts get added together. So we add the 3 plus the 5, and we add the 2 and the -3, both in front of the i's. It's really like just combining like terms. So I don't even need to go to all that trouble. I can combine my like terms. 3 plus 5 is 8. And as I combine the imaginary like terms, 2 minus 3 is -1. So I can write that as -1i, or I can write 8 minus I. Next, I want to do a multiplication. So to do the multiplication, I am going to go ahead and use FOIL, just like I would to multiply any other two binomials. So as I work through my FOIL, I get first is 6, outer is 3 times -2i, that's -6i, inner is I times 2, that's plus 2i, and then last is going to be -2i squared. I need to do one thing before I combine my like terms, and that's to deal with the I squared. We saw the definition earlier. We know that I squared is equal to -1. So I'm going to replace I squared with -1. So I get the 6. I can combine my imaginary terms. So -6 plus 2, that would be -4i. And here I get -2 times -1. This guy ends up to be a +2, and I have a couple of like terms there, and I get 8 minus 4i. So 8 minus 4i is our answer. Put a box around there, it's a lot of mess. Let's do the next one. So again, I'm going to multiply these together using FOIL, but I notice that I have a sum and a difference. These turn out to be a conjugate pair. One's a subtraction, one's an addition, but otherwise the terms are the same, which really is a difference of squares. I'm going to show you the long way because the long way always works, and the long way is just go to FOIL. So as I FOIL this guy, I get 4 times 4, so that's 16. Outer is plus 4i, inner is minus 4i. Last is minus I squared. We end up with a difference of squares because these cancel. We end up with 16 minus I squared, but I squared is -1. So we get 16 plus 1, which is 17. So we can get from these imaginary values, so I can get from a 4 minus I to something real by using that conjugate pair. Okay, we're going to incorporate that into part D. So for part D, I want to do this division, but it's really not going to feel like a division at all. I'm going to go ahead and take this fraction, and I am going to multiply the denominator by the conjugate pair. So I want to use the conjugate. I want to make the denominator real. Conjugate, I want to get the denominator to be a real number because I can work with that. So I'm going to multiply top and bottom. Let me grab a red pen here by the conjugate 4 plus I. I multiply top and bottom because 4 plus I divided by itself is actually 1. So I'm just changing the way this looks, not the value. As I multiply that denominator, it's exactly what we did here in part C. So I do get 17. In the numerator, I'm going to go ahead and just use FOIL. So working through my FOIL, I get 24. Outer is plus 6i. Inner is plus, let's see, that would be 36i. And then last would be plus 9i squared. So we get 24. Combining these, I get a 42i. 42i. And the plus 9i squared becomes minus 9. All over 17. So 24 minus 9, that's going to be 15. So 15 plus 42i all over 17. I'm going to go ahead and split this fraction up. Both the real part and the imaginary part need to be divided by 17. So I'm going to write my answer here. I get 15 seventeenths, that's my real part, plus 42 seventeenths I. So it really didn't feel like division at all. Instead, we were working through multiplying by that conjugate pair.